Okay guys, in this video what I want to do is quickly run through the idea of flux, okay, specifically electrical flux. So we're going to start out with this idea that field, okay, when we draw these field lines, you guys have seen this through your electric fields already. Um, these are like arrows, they can pass through things, right? So in the beginning, what we did is we would place a charge in here. Maybe this will be my positive charge, and then this field would kind of act on this charge, right? So it would interact with it to create some force. What we want to do now is just consider the field itself, okay, and have some sort of measure for how much field is passing through a certain area. So here I've drawn kind of a window for us. And what we're going to see here is that this field is going to pass through this area so that this will be the measure for us to discuss flux. So this flux is pretty much a magnitude of how much field is passing through a certain unit of area. Okay? So first off, I want to discuss this just in terms of what we have here. So my flux, I'm going to go ahead and write this as this variable here looks like a capital I with a circle on it. This is flux. Okay, let's go ahead and this right here is my flux. And this, okay, very simple, is going to be depending on two things. The first is my electric field, right? So how much electric field is passing through? If I increase the amount of electric field, the strength of the electric field, there's more passing in through this window here, right? And the other thing that affects the amount of flux through a certain window is going to be, of course, the size of the window. If I grab this window right here, and then, oops, sorry, this didn't work the way I thought it would. But I make my window bigger, right? So if I make this window much bigger, let's go ahead and do this right here, where I have this much bigger window, okay, you can see that more electric field would kind of fit through there if it was, if the source did kind of extend out here, right? So this is also affected by the area of the window that I'm going through. So let's go ahead and do this. This is also affected by my area. I'll call this A. Now, there's one simple way that we can determine here one more thing that will let us know exactly how much flux is going through, and that is what is the angle of my window versus my field. So what I'm going to do is I'm going to draw this from the top perspective, from the top view right here. Right now what I have are my electric field lines, okay, and the window that I've drawn from the top would look like this, right? You can see here now when we look at this top view that all of my electric field lines are kind of going through like this, right? But what if I were to come at this at an angle, right? So either I change the direction of my field or I change the direction of my window, and my window is now something like this, okay? So in this case, I've drawn it so that it still covers everything, but maybe once I start to twist this thing, it won't reach all four of these vectors, right? So maybe it'll be something like this. So one of them is now left out because of the angle, right? So it doesn't capture everything that it did before. So this angle right here matters, right? You can especially see this in the extreme case, okay, where if I take this whole thing here, what if my window was parallel to my field? In this case, it doesn't even matter how much field there is. It doesn't even matter what the strength of this field is. It doesn't matter how much more we add on or what the length of these vectors are. None of them are ever going to go through the window. So my area doesn't even matter at this point, right? Because nothing is going through. And the way that we we'll give this a notation in our formula is by doing this dot, right? So you guys have probably seen this before. I have my dot product, okay? But a simpler way for us to write this so that you guys remember this is going to be that I have my electric field, I have my area, okay? And I'm going to put in my my formula that will give me the value when it should be 0 when this is parallel. So we'll say 0 degrees, okay? And it should be 1 when it is perpendicular, right? But what I want to do, since my normal should be perpendicular, we're going to call this 0, and so we're going to measure our angle like so. All right, so this is just the convention that we use. This right here, okay, this is my 0 degrees, my normal to my to the area of my window, right? So when I turn this, window kind of like this new angle right here, this will be the amount that I've turned my area, my window for me, right? So we can do this where I want it to be completely full at 0 degrees and then completely 0 once I turn this thing 90 degrees, okay? So the way I'll write this out here, my cosine of 0 is 1 and my cosine of 90 is 0. So what I'll do is I'll put cosine theta. Oh, sorry. This should be on my bottom formula right here. Cosine theta. So you'll see this, but there's just different ways to notation. It depends on what I describe as my theta. If I want my angle to be along this direction right here, and let's say I call this, phi, then this right here would equal 0 degrees, and then out here would be 90 degrees, would be two different things, right? So we want to just make sure you understand that this is the angle between the normal of my area, whatever my area surface is, normal to that, and then my electric field, okay? So this is why for a lot of our electric flux problems, it's going to be very useful for you guys to draw a picture so you make sure that you have an idea of how much field is going through a certain area, okay? And then secondarily, what we want to do is discuss this in a slightly different way with Gauss' law, which is right here. So imagine that I have a charge placed, and then we draw some imaginary sphere or surface around it, okay? Then in order for us to measure the amount of field that's going through this surface at any time, because now my surface is not a window, but it's actually a curved surface, right? So this entire area is what's going to go through. So in this case, all we do is we take the integral of all the field that's going through any unit area, okay? And we do that over the entire surface, over the entire area, okay? Over my entire area, and then this should actually equal just whatever charge is inside divided by my epsilon naught. And remember, guys, that my epsilon naught is 8.85 times 10 to the minus 12, right? So these are just two forms. You might see this here, okay? But mostly we're going to work with flux in this format right here. Just wanted to give you guys a view of both of these as we move along.